The heat of fusion, which we showed on the previous pages, is actually listed as delta H fusion. It's the change in enthalpy during this process. It's the energy required, and it's endothermic, to change a solid at its melting point to a liquid, and it has a value. The heat of fusion for water is 6.01 kilojoules per mole. The heat of vaporization now, or the change in enthalpy during that process, is defined as the energy required, again it's endothermic, to change a liquid at its boiling point, notice how the temperature is constant there, to a gas. And that's going to be 40.7 kilojoules per mole. Note the difference. Why is the heat of vaporization much higher than the heat of fusion for the same substance? So take a couple seconds to think about that, write down an answer or discuss it if you're with somebody, and then we'll move this box in a second. Okay, here we go. Now, to change phase from a solid to a liquid, strong bonds are replaced with weaker attractive forces between the particles. The energy change isn't that big. When a liquid changes to a gas, all attractive forces are broken. The energy change is very large, so the heat of vaporization here is going to be much larger than the heat of fusion. Let's have these processes going the other way, in which case they're exothermic. They are releasing energy. The heats of fusion and vaporization apply here also, although the names don't make as much sense. But the first case, we have a liquid going from a liquid to a solid, and it has the same heat of fusion when you go in the other direction, 6.01 kilojoules per mole. Sometimes that's called the heat of solidification, but we're just going to keep it with fusion because it's the same value, and we'll get to the bottom in a second and tell you what happens to the sign. Now, when you release energy, when gas goes to a liquid, so you have gas condensing to a liquid, we have the same value for the heat of vaporization there, 40.7 kilojoules per mole. Sometimes that's called the heat of condensation, but we're just going to keep these two descriptions, fusion and vaporization. Now, I talked about a sign earlier. We don't have a negative here. How come? Because we know it's going in the opposite direction. Well, the negative is implicit in the word released. That tells you have a negative sign. If we asked you for an enthalpy change, then you would say it's a negative heat of fusion or a negative heat of vaporization. We're going to have to work problems here to have this make a little more sense, but please review this slide before you get to the problems. We're going to compare the heats of fusion and heats of vaporization for a few common substances. We start on the left here with butane, then diethyl ether, water, and mercury. And on the y-axis, we have the heat of fusion and vaporization in kilojoules per mole. You can see in each case how the heat of vaporization is greater than the heat of fusion for each compound here. And you can also see that mercury takes the most energy to do phase changes, right? You have 23 kilojoules per mole for the heat of fusion, which is greater than the other guys here, butane, diethyl ether, and water. And its heat of vaporization is higher than the other three samples here.